Welcome to week 2, day 3 of IS50B. We're going to continue talking a little bit about the computer science behind the development of games. Let's see. Okay. So of these, which one of these things do you think you guys can write? Do you think you could write a function that would detect if two axis-aligned bounding boxes? Let's unrotate this. Yeah, that's fine actually. Do you guys think you could write code to detect if Mario hit a question block? All right. Everything in a 2D side-scrolling Super Mario Brothers game is just a rectangle. Mario's rectangle or square probably. I don't know. All the blocks you hit with your head or squares. Do you think you could detect when Mario hits something? Okay. Then after you hit it, what happens then? So if you're small, you bounce, right? And so you have to maybe do a little animation on the block. The block will kind of go up a little bit like that if you hit it. It doesn't break if you're small Mario. If you're big Mario, the block breaks, and you have to delete it from the map so that you can then move through it the next time you jump up through it. You also have to, there can also be multiple blocks in a row. And so this is one of those things that is always like hard to really get done right, which is collision detection, right? Like let's say you have two blocks in a row and Mario jumps and hits both of them, right? Then what happens? Do you get both coins? Or does Mario only, it's very slightly not lined up, it's bothering me. It's like 1 pixel off. How would you handle that, right? I'm actually asking you guys, how would you handle that when I'm trying to line this thing up? Dang it. Actually, I think I had that one lined up. Whatever. The first one hit, but you hit both because they're on a, let's say you have a row of boxes, and this is Mario here, and he jumps up. Which one breaks? Break both, maybe. Yeah, it's. I think the way that they handle it is that there's actually a picture of Mario jumping with his fist up like this. I believe that whatever block is above the fist, like that one, would get broken, I think. And then, but if you overlap, you still have to push Mario back down. He needs to bounce off of it, and so he breaks the box and then falls back down. You can't ever have overlapping, sprites like that. Maybe if you're stomping on a Goomba, or if you're stomping on a Goomba or a Koopa or something like that, maybe you can allow overlapping. But for landscape, you basically never allow things to interpenetrate each other. And if they do interpenetrate each other, like this, then you've got to find the nearest open spot and push them back out. Of course, that leads to the problem where people fall out of worlds in 3D games because sometimes a door opens into you, and then the nearest open spot is beneath the ground, and then the engine throws you through the floor, and you fall to your death, or you fall forever, or whatever. So, so axis-aligned bounding boxes are pretty easy to code. If I were to explain it, so every axis-aligned bounding box just has a minimum x, a maximum x, minimum y, and a maximum y, right? That defines the 4 sides. Sometimes you'll see it defined as a point, x, y, as the top left corner, and then an x size and a y size, which is equivalent to having x min, x max, y min, y max. It just depends. Which one you pick just depends on which way is going to be faster for you to do the computations, depending on your algorithms, really. Great, thanks, Bazooki. So, AABBs are easy enough that, first semester students can can write them, you know, with a modest amount of trouble. Triangles, yeah, triangles start getting into like more annoying territory. Again, usually you slap a AABB around them, test that first, and then only if they overlap, if their boxes overlap, then you do the more expensive intersection tests. Okay, circles touching. We didn't talk about that last time, but that's pretty darn easy as well. If you have a circle, and let's switch the color to be red. You have a circle, and you have a circle. Then it's pretty easy to figure out if they intersect. You got a center point, and you got a center point. And so you can compute the distance between the two of them, right? You guys know how to do that? Distance between 2 points. Pythagorean theorem, that's D. And so you basically check to see if the distance between the 2 points is less than the sum of the radiuses. Right. That's it. And the distance does involve a square root. It is the square root of this squared plus the square. And so you can compute this quantity squared, and so you can actually do this comparison instead. Squaring something is a lot easier than square rooting something. Square root could be 70 or 80 cycles on your CPU. Squaring something is going to be 4, maybe. I don't know. Depends. Depends on your architecture, but that should give you a ballpark idea. Squaring something is roughly 10 to 20 times faster. So it's very common for, especially if you're doing a lot of these things, for people to compare the squares instead of the square root. Okay. Because it doesn't affect the inequality. You guys with me on this? Do you understand the theory? You got radius 1. Radius 1's this big. Radius 2. Drawing with a mouse is kind of annoying. Right? And so basically, if the distance is smaller than the sum, there's going to be some overlap. And if you're like, is it less than or equal to? Again, depends. You tell me. I don't know. If 2 circles are touching, are they intersecting? I don't know. You know, with floating point math, there's error in there, and so in practice, it might matter, it might not. It's not something to worry too much about. Okay, and the same principle applies to a sphere. So if we were to take a sphere, yeah, look at that. Check me out. So you got a sphere, and you got a sphere. Where'd the colors go? Good. Well, take a pickup. How's that an oval? Yeah. So you got 2 spheres. There you go. That's nice in 3D. Same principle. Same exact algorithm. Compute the distance. The distance is going to be a 3D distance instead of a 2D distance. So you got an extra square, an extra add in there, an extra subtract. But same principle. You just add up the radiuses and compare that against the distance. Is the distance from R1 plus distance of R2 less than R1 plus R2? Is the distance? No, you got the radius. Every circle or sphere is defined with 2 numbers. You've got the center point. I don't know. I'll just call this point 1. Point 1. And you got a center point, point 2. And so you take the square root of point 1 dot x subtracted from point 2 dot x quantity squared plus the same for y. Right. Point 1's y minus point 2's y. I hate drawing with a mouse. It's super annoying. Like that. So that's the distance. So the distance is x1 minus x2 squared plus y1 minus y2 squared, quantity square rooted. That's the formula to determine the distance between P1 and P2. With 3 dimensions, you just add on another term for z. Yep. It's the hypotenuse. Yeah, it's the hypot function. So in standard C++, you have hypot. That's the Pythagorean theorem. And so you just basically compare the distance between the two of them with the sum of the radiuses, the radii. And that will tell you if they're intersecting or not. So actually, when I wrote my collision detection engine, everything was a sphere. I didn't even use axis line bounding boxes. I had mechas, and the mechas were all relatively spherical, kind of. In areas where they weren't, I used a hierarchical system. So what I did was I would have a giant sphere, and then I'd have smaller spheres inside of it. So like if I had a mecha that looked like this, like from the front, it looked like this kind of, had some guns sticking out of it, I don't know. Yeah, maybe kind of like that. So what I had was I had one sphere for the upper half, one sphere for the lower half. The spheres kind of overlapped in the middle here, where it was narrower. And that was actually a pretty decent approximation to the hitbox on it. And so if I wanted to see if something hit it, it's really easy. You just do a sphere versus sphere test. And let's see, is the distance smaller than the sum of the radii? If so, yeah, they hit. And so I had one big sphere like this around it. And then if that was hit, then it would test the smaller spheres. And so like if it was over here, it would register as a miss. Because that spot, while it did hit the big one, it did not intersect either of the children. And so that would be a miss. Whereas a shot here, it would first test against the big sphere, yes. Test against the child sphere, yes. And so this would be a hierarchical bounding sphere, I guess you'd call it. Does that make sense to you guys? And my entire game engine used spheres just because it was easy and fast to compute. I think I had direct collision on the landscape. So the landscape was a series of triangles, obviously. So that was all not spheres, obviously. But otherwise, pretty much everything was a sphere in the world, all the objects in the world. So Binninghoven saying Bazookian, does that make sense to you? Like it's a pretty easy way to see if two balls are overlapping, Okay. And then in 3D, 3D is basically the same for an axis line bounding box. You just have x min, x max, y min, y max, z min, z max, and you just see if there's any overlap between them. Okay. So yeah, and so it's very common when people are coding to just stick to that. We talked about cylinders last time. A cylinder, you first check to see it's kind of a combination of a circle and a bounding box, right? So you just check to see if the point is between z min and z max, so that's like an axis line bounding box. And then from the top down perspective, you check to see if the x and y is within the circle. And so you can combine a axis line bounding box and a sphere to get a cylinder, or a circle and a box. Essentially, if they have a child, it's a cylinder. And so that's actually very, very easy to do too. It's a radius test for if you're looking at it from above, you use the x and y to see if it's within the circle, and then from the side, you see if the z is between z min and z max. And so cylinders are very commonly used for people. Okay. Yeah. So it gets more complicated once you start getting into convex holes. And I guess we should start with like a line intersect test. Do you guys remember how to do that? So if you got one line and another line, do these lines intersect? Do they intersect, right? Do you guys remember that from algebra? Line intersection test. Can't you get the slope? Yep. Every line can be defined, well, especially as a line segment, which, you know, all these things are line segments. They're not infinite length lines. They're line segment. You're going to have an x1, x2 down here. You're going to have x1, y1 down here, and x2, y2 up here. And so you can compute the slope of it, right? So what is the slope of a line segment? Zero. It's y2 minus y1 quantity divided by x2 minus x1. Right, so if it goes up 5, so like let's say y is 5 higher and x is 1 to the right, so that it have a slope of 5. Right? So that's m. I don't know why they use m for slope, but there you go. Y is equal to mx plus b, all right? And so that's m. Let me make the font a little bigger. That's the slope. So y2 minus y1, x2 minus x1 is the slope. And then, do you remember how to do the, and then you can do that for both, right? And so, do you know how to compute the intersection? 2 lines. What if you want more detailed work like I'd hit in one arm? Yeah. I'll go into that in a little bit. So it is mx plus b is equal to mx plus b, but we have to do a subscript on that. I don't want to use x1 and x2 again. I'll call it a, I guess. Ah, damn it. Q and R, I don't know. I'm running out of variable name. Yeah, so you basically just set the equations equal to each other and you solve. So line intersection. Yeah. And so you see if you can solve for that, and if they intersect, congratulations. Okay, so to see if a line intersects something, like let's say, and this is very common for like a gun, right? Like you shoot a gun like that, does it hit the box? There's actually an even easier way when you're dealing with boxes, especially an axis line bounding box. You could do the line intersection test, right? Like you could do this for each of the 4 edges of the box. Can you guys think of an even easier way of doing it? How can you tell if Senior Red here is intersecting this box? So let's say that x minimum here is, say that x min is equal to 5, x max is equal to 10. Y min is equal to 0, and y max is equal to, it's a box of 5, I guess. Okay. So can you explain x min and x max again? Yeah. So this is a box, right? And so yeah, it's the corner values. So we add a new coordinate here. Well, to define a box, you actually you need 2 points, right? So this guy, get rid of, delete him. Draw shapes. Use edit to add more points.
Draw my coach.
Okay, so for this box here, the minimum x value is 5 and the max is 10. Minimum is 5, and I think the minimum y was 0. And the max was 10, and the max y was 5. Yep. So these 2 points here define a box. You don't actually need to write down all 4 points because it's a rectangle, right? And so typically you hold a rectangle in one of 2 ways, either as one of the points and then how much to the right and how much up it goes, or you hold the min and max, right? So this is the min. This is the minimum values, and these are the maximum values.
It's my couch now.
Okay. So snap, that might be nice. Snap. There we go.
Hey, you're supposed to stay on this side of me.
There, perfect.
Do you like how I just stared at you?
Let's get rid of you. And there we go. So we got a box. Now, so this is the box we have over here. Does that make sense, Binninghoven? So you got x min, x max, y min, y max. That defines the box. Okay. And now we've got this line. So let's say we've got a bunch of boxes out in the world, and they're going to be cubes in 3D, but basically 3D adds, like, it's the same thing. All right. You just have one more check. Instead of x and y, you have x, y, and z. It's just extra typing, so I'm just going to do it in 2D. So let's say you've got this line here, the person shoots a laser, and you want to know, did it hit the box? Okay. The slope of this line, let's say, is, a line equation is y is equal to mx plus b, right? A little bigger. So let's say that the equation y is equal to 3x plus 1. That looks maybe 2x plus 1, whatever. Okay, so that is the line, and we want to know, did it hit the box? Okay, you could do that line, segment, intersect, but you don't need to, because there's a really nice property when something is axis aligned, right? What you can do is you can just plug in what is the value of y when we're at x minimum. Can you guys solve that? What is the value of y when we're at x minimum? So when x minimum is 5. Okay? So when x is 5, what value is y going to have? 11. Okay? Is 11 between 0 and 5? Nope. So our thing is going to be like up here somewhere, right? And then as long as it's not a vertical, yeah, you'll have to check 3 of the sides? 2 of the sides. 3 of the sides, I think. Yeah, you have to do that for 3 of the sides. You don't have to do it for all 4. Okay, so for x max, what value does y have when x is 10? 21. Is 21 between 0 and 5? Nope. So it's up here somewhere. And then we'll do it for, like, let's say y minimum down here. So when y minimum is 0, x is equal to negative 0.5, right? If I'm doing the math right. When y is 0, x is negative 0.5, right? Okay. Is negative 0.5 between 5 and 10? So it's a miss. You could do it for the other one as well, but I believe you can't draw a line through a box without hitting at least 2 of the sides, right? Like no matter how you draw a line through it, it's going to hit, if it hits at all, it's going to hit 2 of the sides. It's got to go in, it's got to go out. So you don't have to check all 4, you only have to check 3 of them. Okay, so do you guys see that? So you just put one value for x in, and then you see if the result is between the values of the other axes. So you plug in x min and check to see if the result is between y min and y max. You put in x max and check to see if the result is between y min and y max. Then you put in y min and you check to see if the result is between x min and x max. Or you can put in y max and check to see if the result is between y min and y max. If any of them are between, then you've got to hit and you can stop. So if for example, our equation was, let's say it's just got no slope whatsoever, 0x plus 7, then we plug in x min equals 5. Oh, wait, shoot, not the other way around, sorry. 2. There. We plug in x min as 5, we get y is equal to 2. So that's a horizontal line going this way. Congratulations, it's a hit. You don't have to do the other checks. All right, so you do a multiply and an add. You do a multiply and an add, and then an if statement. And then if you get a hit, you're done. Otherwise, you do a multiply and an add, multiply and an add. You do 3 of those. Congratulations. You've now figured out if a line touches a bounding box. Do you guys understand? And so this is called line casting or tracing, or let me delete this. Let me delete this river that I got down here. Oops, I accidentally selected the high pot.
I found you, Brian.
Ah, dang it.
I don't know where it is. I'm just gonna sit down.
Delete.
The moment I said I found you, I found you.
Delete.
I really said I found you.
Like a peasant.
You didn't move,
Look
so
at
I'm
this.
like,
All right.
are you there? Because the reason why, because I know that's
Okay.
What? No,
So this is
I'm
called a
like,
line
I saw
trace,
you,
right?
I said, I see you. You didn't move, so I'm like, I'm gonna just.
And so a very common one is line versus axis line bounding box. That's what we just did there. Very easy to code, very fast. People that get really into like, guys. Brian, say hi to my students. Okay. Kayla, I'm gonna check. Okay. So this is a very fast check, and like I said, people that get into computational, kids. Okay. People that get into computational geometry, they probably have an even faster algorithm, and that doesn't bother me too much. It's fast enough. And if you really want to get into optimization, there's probably better ways of doing it. So, yeah, but that's easy. Okay, so line versus axis line bounding box. Then line versus circle. So if you want to see if a line touches a circle, like that, what you do is you figure out the point of nearest, the point it's nearest to it. You do that by, you can figure out the normal from the center to the line, and then you see if the distance of that is within the radius of the within the radius of the circle. So this is something called a projection. Let's scroll down a little bit. So if you've got a, let's say you've got a ground, right? This is a very easy projection to do. And you've got like the sun, and the sun is like shining on a box. A projection is, where does the shadow fall? Down here, right? So that's a projection. And projections can be done using the dot product. And so you've got this vector here, and then you've got a vector here, and then the dot product will tell you the point on the line. These don't have to be horizontal either. Like they give you like this, and so it'll project onto the point. And so once you do that, once you know where the nearest point is, then you just basically take the distance here, and you say, is the distance less than the radius? Cool. It hits. So you don't have to check all the points on the line. You just do a projection, get that point, and check to see if it's smaller than the radius, or more likely, yeah, you know, it might be another one of these things where you check against the squares for a little bit of optimization. So if you want to see what that looks like mathematically, dot product projection. Got a high resolution image there. So you've got your line here, and you've got the sun, or you know, whatever sphere. That's the center point of the sphere. And so you take the dot product of this and this, and it gives you this point here. And yeah. So that's easy. It's got a cosine in there, I believe. I think you can do a dot product without a cosine also, using a couple of multiplies. So pretty easy check also. It's going to be a multiply, and add. Might have to square it. Either way, not too expensive. Not too expensive. Okay. But now, let's see, is there anything else? Cylinder. Cylinder is just a combination of the two. Convex hole. So versus a convex hole, there's probably a faster way of doing it, but if you've got a line coming through this polygon here, you just do a line intersection test with each of the 5 lines. But I would first test this shot against the axis line bounding box. Discard it if it's a miss. If it doesn't intersect the axis line bounding box, you just say miss. If it does hit, then you can do a line intersection test against each one of these. This thing here. Okay. So, do you guys feel like, I don't know if you're gonna have to code this. Maybe I'll have you code it. But what do you got here? Check collision. What do we got here? See if a line touches or intersects outside a circle. Okay, can I open this? Okay. I'll just copy and
Come back to the couch spot. No, it's right to offer some weak there.
paste. Okay. So given A, B, C, X, Y radius, fantastically unhelpful names. If you're gonna have names like this, you gotta tell me what A, B, and C are, dude. Like, come on. All right. I mean, I can guess, but massively unhelpful coding spell. Okay, int distance is equal to the absolute value of A times X plus B times Y with a slope maybe, or plus c divided by the square root from a to b. So that's squared plus b squared. Okay. Maybe that's the dot product. Checking the distance is less than the thing, touch, intersect, outside. Okay, so 3, 4, 25. So maybe that's the center point, and maybe that's the starting point of the line segment, and the angle. Yeah, this is why you should name your variables something good. Yeah, but that's the equation right there. Okay. So yeah, it's something like that. Okay. So there you go. Yep. It's not hard. It's like it's basically that one line of code to do it. All right. So that's what 4 multiplies, 3 adds, a divide. Divides are kind of expensive. Square root's kind of expensive. So I'd probably save the radius squared to get rid of the square root. Yeah, not too bad. Not too bad. Yeah. A, B, and C are the constant. What constant? Like, what's x? What's y? What's the slope? Like, it bothers me. It bothers me when they don't. You know, dist I understand. Dist is distance. That I get. You know, ax plus by equals c. Okay. All right. Yeah, that makes sense. Okay. Okay. So c is the plus b. So what I've been calling b is c, and they have the slope instead of m. They have it as a and b. Okay. All right. Got it. Math people like their single letter values. Shouldn't it be s? It's a slope. Okay. All right. So that. Okay. Now let's get into the real stuff, right? Line versus BVH. Okay. So BVH is one of 2 or 3 most common ways that you store objects in a world. So what is a BVH? What is a BVH? Beverly Hills. Beverly Hills. BVH equals a bounding volume hierarchy.
Did you get full by my thing?
Let's spell hierarchy. I before E except after C. There we go. So, what is a bounding volume hierarchy? Well, this is to answer the question that Ezekiel had earlier. What if you want like nested bounding volumes? Well, that's a bounding volume hierarchy. So, like what I had with my mecha, did I delete it? No, here it is. I had a enclosing sphere, a big sphere enclosing the whole thing that had smaller spheres inside of it. And so when you do a test to see intersection or something like that, you first test on the big thing, which makes it very easy to just throw away a miss. Like if a bullet flies past, a mile past you, there's absolutely no reason you should be doing any more computations than that. It missed. Cool. So a BVH is anytime it's basically required for RTX on. So if you're doing ray tracing, your level is going to be basically held in a BVH. Imagine you've got, you know what, I'm just going to pull up a picture of it. It's easier than me trying to sketch it with my terrible art skills. So you have one big enclosing volume, and then you've got smaller volumes inside of it, and those, if they're not too accurate, can have smaller volumes inside of them as well. And these are super useful. Yeah, okay, that's closer to what I was talking about. Okay, so let's say you've got a warehouse or a level or something like that. You see how there's like this one big rectangular prism. It's big, we'll call it a rectangle, whatever. We got this big rectangle because we're working in 2D. We got one big rectangle enclosing the whole thing. And then for the smaller areas, there is a rectangle enclosing that room. And then for the curved surface, there's a lot of rectangles. You see that? So there's rectangle and a 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 rectangle. And so curved surfaces are really annoying when you're dealing with axis-aligned bounding boxes, because if you have a 45-degree angle, you have to keep making more and more boxes, and you have like an error. There's an amount of error that you're willing to accept, right? And so if this whole level was just one giant rectangle, we would just put a rectangle around it and be done. But we can't because there's too much open space in here. And so there's probably going to be, yeah, so right here, you see this green line here. That encloses the entire right side of it. So if I were to shoot a laser right now, and it goes straight through the middle, like right where my mouse is here, I'd first test it against the enclosing box, and it would be like hit. And then the enclosing box might have 3 sub-boxes. Sometimes it's like a binary tree, sometimes you allow multiple kids, it depends. There's a lot of different ways of doing BVHs. But you see this kind of green, here let me save this. And let me open it. Okay. So let's say I'm shooting a open with Microsoft Paint. There we go. Okay. So here's Microsoft Paint. Best paint editing editor ever. Okay, so let's say I'm shooting a laser. Let's say I'm shooting a laser and I want to see if it hits the world. And it's kind of going down, like it's kind of going down at the RTX on there. It's going like kind of down, like it's shooting out of my eye here. It's shooting out of the camera, and it's going towards that point there. I can't draw in 3D. Maybe I should have used Paint 3D. Okay, so anyway, so guys, and so there's going to be we first tested against this box here. You see the yellow line here? It's going to first test against that because that's the enclosing bounding volume hierarchy. And then the enclosing one probably has 2 kids. Okay, it's got 2 kids. It's the green line here. So this is the left kid here. Do you see that rectangle there? And then it's got a right kid here. Okay. And so I test this line against both of them. And it hits the left one, it does not hit the right one. Okay, so I can ignore all of this geometry here. This is really important because there's a lot of geometry over here. You do not want to have to do the line versus axis line bounding box for all million boxes within your level, right? It's, even though the test itself is fairly quick, if you're having to do that multiply and pow and minus, and if you have to do that a million times for every time somebody shoots a bullet, your gameplay is going to be really, really slow. What you want is, rather than having to check every box in the level, you want to check log base 2 of the boxes in the level. And you'll see that over and over again in computational geometry. If you can get the running time of an algorithm up to about log base 2 of n, where n is the number of boxes in the world, then it's fast enough.
That looks cool.
Yeah, logs is atom.
Logs are very, very fast.
Changeable.
So, yeah, and so this is a level. And so if you have a million boxes in the world and you want to see if any of them hit, if you can do it in a log base 2 n time, you only have to check 16 times or so, right? That's
Bart was telling me the same lesson.
Yeah, every time you double the number of boxes in the world, you only have to do one more test. And so that's really, really good. It's the opposite of exponential, right? So if we do a log, that's log base 10, right? But the fact remains, every time you double the number of boxes in the world, you only have to do one more test, and that's really, really good. So we come in here and we see, okay, the left box here has been hit. Okay, so now we're going to check the two sub boxes of that one. And it looks like the two blue ones are the two sub boxes. And so we've got one box here. I'm drawing it on the screen for you. Actually, it goes up a little bit further. So right here. And then it's got one on the left here. And it misses this one, it hits this one. Okay, cool. And then it's going to be divided, I think, on that teal line there, maybe. It's kind of hard to tell, everything's really overlapping. Yeah, so let's say we've got one here, and maybe another one up here somewhere. It doesn't hit either of them, it misses. So with one, the yellow, the green, the blue, and the teal, or the light blue rather, it's not really teal, with just 4 tests, we're able to see we missed. So even though there might be a million different boxes in here, because we're using a BVH that's set up properly, and how you build a BVH is actually fairly complicated. And we're not going to go into that now. You just need to understand what they are and how they work. Once you've got the BVH built, hand wave, because there's a lot that goes into it, right? Because there's a lot of different ways you can build it. You know? And there's a trade-off between having a bigger tree and having better accuracy and things like that. But basically with just 4 tests, 4 axis line bounding box versus line tests, which are fast, we could say miss. And we don't need to go through all 1 million other things in the world. This image is hard to understand. So these are axis line bounding boxes. Each one of these things you see here is a axis line bounding box. But they're hierarchical, they're nested within each other. So you got a big box, the yellow line here is the big box that encloses everything. And then the green boxes are the 2 children of the big box, and then these blue boxes are the 2 children of the left green box, and then the teal boxes, or light blue I should say, are the 2 kids of that one, and so on and so forth. And then once you get down to the nitty gritty, you can see there's just boxes like literally everywhere. But they're all set up in that sort of tree fashion. Okay. And so, yeah, and so if they only had a few layers, it'd be probably a little bit easier to understand. Let's see if I can find another one. Yeah, here we go. It's sort of streamlined. So this one has 3 kids per node. And so you have one box that encloses the whole thing. That's the root node of the tree. And then it's got 3 kids, one for this area up here, one for this area over here, one for this area over here. And again, how you cluster them and stuff like that, like there's a lot of different techniques you can use for that. You can do bottom up or top down BVH creation. Doesn't really matter right now. And so if I were to shoot a line at this, save images over there, and open you up with paint. Okay. So again, let's say this is the top-down view of the world. I'm a little person here. Yeah. And I'm going to shoot a laser this way. Some sort of hit scan weapon, right? Let's give me some arms too. There we go. So first thing you do is you say, does this line segment intersect the root node? Yes, it does, right? The root node is this enclosing bounding box here. It certainly intersects. So then we check, does it intersect this one? Nope. Does it intersect this one? Nope. Does it intersect this one? Yes. We found an intersection here. So then we can ignore this one, we can ignore this one, we only need to look at this one. So then we recursively go down inside of the tree, and we say, does it intersect this object here, C? And maybe we do an expensive test there where we do all the more accurate intersection, and we're like, yes, we hit it, and that point right there is the point of intersection. So by doing this, you can very quickly navigate through a world, and yeah, here's the classic bunny one. you can very quickly navigate. So this would be a bounding volume hierarchy with just two boxes. This one has more accuracy, but more tree structure. This one has more accuracy, even more, you know, and it's just a trade-off versus how accurate you want your BVH to be versus how deep and how big, because you have to store these, right? And so every time you load it, you've got to either load this or you have to recompute it from scratch, which takes time also. So does this make sense to you guys? Does this image make sense to you? Binninghoven, Singh, Buzikian. So you got a bunny, right? Binninghoven, you got a bunny, and I want to see if I'm going to hit the bunny when I shoot. So if I just used one bounding box for the whole thing, I would hit it if I hit here, right? You'd be like hit, and that's not very accurate, right? And so if you do a BVH, you have one box enclosing the whole thing, and then you've got smaller boxes inside of it, and it keeps going down and down and down. So when you get over here to the right-hand side, this is a very detailed BVH. When you check to see if you hit this spot right here where my mouse is, it'll say miss. Here it would say miss. Here it will say miss. But on this one, if I have a very inaccurate one, if I shot between its ear and its back, it would say hit. Okay. So, you know, it's a trade-off. It takes longer to do an accurate collision like this, but there's really not very much error on this, right? Like, if you shoot a bullet and it barely nicks the ear but doesn't really, and it registers a hit, nobody's going to be able to see. Even on this one's pretty good. Like if I shot right here, it would register as a hit, but who cares? You know, it's like, it's pretty good. It really just depends on your needs. And so it can, yeah. I mean, this is a bunny, and you've got, I don't know, like 100,000 maybe boxes here. That's 100,000. You either have to do 100,000 loads, you know, off disk, right? You have a file that contains all the Xmin, Xmax, Ymin, Ymax for each of these, right? And the tree structure, right? The index 100 is my kid, index 500 is my kid. So you're talking about 6 numbers. So you're talking about 600K, maybe, for this. Maybe more, right? Maybe 2.4 megabytes. You know, that's not instantaneous, right? Or you just load it and you do the BVH calculation at load time. You're seeing the appeal of low poly games, yeah. The art's cheaper. Yeah, there you go. You can see it doing a collision test here. The art's cheaper, and it's faster to do accurate collisions with them. So, and so you need to do a BVH actually if you're going to be doing RTX. The RTX acceleration on a 20 series or 30 series graphics card, it is doing this. It does that in hardware. So if you've ever wondered what RTX is, it is hardware acceleration for what we just talked about. And so that's why I said you don't really need to worry about implementing this per se, because what you do is the engine itself will create the BVH for you, and the 3090 or whatever you have is going to accelerate this test. Okay, and so yeah, there we go. Okay. And so that
by the sync.
So you pass the graphics card a BVH, and then you can do a ray cast. In other words, you have a starting point and you shoot a line through the world, and the hardware does it for you. So it does exactly what we talked about in here. It's going to first, find the first box that it hits, then it goes inside of it, finds another box that it hits, and goes inside of that. And so with a log-based 2n operation, it can find the first object that hits, or it might miss. You know, if you shoot it off this way, it'll miss. Okay. And if it's opaque, you can stop at the first one, but if it's transparent, like let's see, you have glass, and you actually need to shoot the ray all the way down. Is there a specified magnitude of these rays? So when you're doing RTX, it's actually a completely different rendering system than a triangle-based rasterization system. I don't know if I want to talk about that today. I guess I'll talk about it today. Why not? Okay. So let's open this up in Paint as well. Use Paint 3D, why not? Okay. So what happens? Let's say you've got a camera here, right? So this is your eye. You know, this is where the player is in the game. What happens when you do ray tracing, when you do RTX? It shoots a ray at every pixel on the screen. So for every pixel on the screen, it gets a ray shooting at it. Okay? And then the RTX accelerator can very, very quickly tell you what you hit. Okay? If it's opaque, it'll tell you that's where you hit. Okay? It's a very, very fast graphics cards are very, very powerful. It can do it very, very quickly. And so if it shoots a ray this way, it's like, okay, you hit that red box there. If it hit here, okay, you hit a green box there. And then it'll draw a red pixel on the screen. It'll draw a green pixel on the screen. That's kind of the simplest way of thinking about ray tracing. Now, the cool thing about ray tracing is when you get into reflections and translucency and transparency and refraction and lighting. So let's say you've got the sun here. You got the sun. This is like a top-down view, right? So you got the sun here. This part of the box is going to be lit. Do you guys see that? Like this area that's facing the sun, it's going to be brightly lit. This area here is going to be like kind of medium lit. This area back here is going to be dark. You guys understand that? Because the sun's kind of shining, right? Likewise, this part of the red box is going to be lit, but this part back here is going to be in shadow because the green box is blocking it. Does that make sense to you guys? We're like looking at it from a top-down perspective. Okay. So how do you do that? How do you know that this is in shadow, right? Like I'm shooting a ray out this way, and it's like you hit here, it's red, and you're like, all right, cool. But how do you know if it's in shadow? Well, what you do is you shoot a ray back at the sun. Okay. And so you shoot a ray from the point of intersection to the sun. It's called a shadow ray. And if it hits something, then you can't see the sun. That's it. It's in shadow. Okay. And if you have other lights, like you got a light bulb over here or something, it's a really garbage-looking light bulb, you could shoot a light at that one. You're like, oh, yeah, I can see the light bulb. And so it'll get light from the light bulb, but it won't get light from the sun. Does that make sense? And so for every light you have, like if I have a light over here, it'll try shooting a ray over there. Nope, sorry, can't reach that one. So for every light you have, do you see that? It's going to increase the number of rays that you have to shoot out. And that's why it's really important to limit how many lights you have in a level, because especially dynamic lights, if these lights can move around, then for every light that you have you can move around, it's going to multiplicatively increase the amount of rays you have to shoot out to see if you have shadows. What if it hits something that has a transparency of 0.5? Great question. So let's say that our let's do all this. Let's say that our green box here is actually translucent, right? Let's say that our green box here is 50% transparent, right? And there's actually two boxes here. There's one here and one here. The rest of this is open, but it's a BVH, right? So there's an enclosing box here, and then there's two smaller boxes inside of it. So Biddinghoven, do you understand that the concept of a BVH? Like we make the bigger box just to make it really fast, to say miss. Okay, cool. So we've got two actual boxes here. So let's say we hit this box here and it's 50% transparent. So, and let's say it's got refraction on it too, right? Like it's a glass, like a murky glass of some sort, right? We got our sun over here again. Sun's shining. We got a light bulb over here. Okay. So we hit here. We have to both, well, we have to do this. Watch. So the ray comes out here, it hits the intersection. So we cast a shadow ray up here, and that tells us, is it lit or not? And it's going to be like, yeah, it's kind of lit. It's at an angle, you know, whatever. Then it shoots another ray this way because it refracts. Right? We've got an index of refraction. When you pass from air into glass, it bends, right? And it's going to bend in the direction of the. Hey, Dad, there's somebody in the front. Yep. It'll bend this way. Now,
how are you?
now, guess what?
This is the spectrum.
There is.
Here to see if the box is working or not, or
The box started working, but I need to do something else.
There is another ray cast, and there's another intersection.
you sure? Because once I come in, I have to start the job.
Yeah.
Now, this one is also going to get a shadow ray cast, and then it's going to refract out again this way. It bends backwards.
The person on the phone was not.
It bends backwards. Please don't take out the internet, by the way. I'm lecturing right now.
I would have to.
You're going to have to? Well, I can call the lecture pretty quickly. So the light will bend out that way. It calls the intersection here.
Yeah.
Shadow ray here. Blocked. And then this one has to cast one out here. So you can see, and then this one will cast a ray out here to see if you can see that light. This one will cast, do you see how that works? And if this is translucent, then it's going to cast another one this way, right? And so if it's somewhat transparent and somewhat translucent and somewhat refracts, it'll actually cast multiple rays. And then these can reflect inside of it as well. Like if this is like another kind of glass, and each one of these are also going to cast refracted rays out like this. And then that one will reflect inside of there. And so you can end up getting an exponential chain of photons coming out. And so there's typically a cap put on how many photons can go and reflect and refract out of it. And that's your RTX quality. So the higher your quality, the more photons you get. Okay. I'm going to wrap it up now. Okay. So that is our thing for today. I will pick it up tomorrow. Okay. They're going to work on the internet, I guess. All right. Hope that was interesting for you guys, and I will see you guys tomorrow.